All right, 2.8 is about circular motion, and the biggest thing that we're going to look at here is, at the start, just to get a feel for it, is this concept of acceleration. What does it mean to accelerate? So in class we talked about acceleration being a change in velocity over change in time. But then we also defined velocity to be a vector quantity, and velocity therefore has magnitude, which I'm going to abbreviate as MAG, plus direction associated with its value. So if you have 20 meters per second, that's the magnitude. But if you give it a direction as well, then 30 degrees above the positive x-axis, then you've also given it a direction as well. So the concept of acceleration is change in velocity. So what happens if the magnitude is changing? That's easy. That's what we've been dealing with. An object goes from 20 meters per second to 10 meters per second in 5 seconds, so that's definitely acceleration. But what happens if the direction is changing? So do you feel that when a direction is changing? And so that gets us to this nice, simple concept of circular motion. So what happens if you were going in a circle and you were traveling along at 20 meters per second? That's your magnitude, but that wasn't changing. So looking at the circle that I just drew underneath the word velocity, you see that your direction is changing. So if magnitude changes or direction changes but magnitude stays constant, or if both change, then you are accelerating. And that's sort of the premise of the circular motion that they're going to be talking to you about. Is we're going to be dealing a lot with a circle. So that's pretty simple. So let's sort of visit a circle and see if we can recall some simple things. In a circle, if you go all the way around, you went 360 degrees. And so you can call that, if you do that in a unit time, you can end up with some simple understandings of circles. So at 360 degrees would be how many? 6.28 radians. So 360 degrees is one revolution, which is 6.28 radians. One revolution, one oscillation, many different ways. Rotation. So all these could be used to talk about circular motions. You could talk about rotations per second, angles, angular speed. So that you could. What if you did? What if it went around this circle in 2 seconds? So you went 360 degrees in 2 seconds, or 180 degrees per second would be your angular speed, 180 degrees per second. And then you could say, oh, well, I know that's 3.14 radians per second, or 1/2 revolution, or 1/2 rotation per second. So think about all these different ways that you can describe circular motion, and then you can start thinking about how you can equate that to linear speed, or the speed that it's actually traveling. If you were to, I always sort of say, if you were actually going in a straight line. So you can say, well, the velocity of this object would be the distance that I traveled. And if you think about distance around a circle, then you are talking about circumference, and that's 2 pi r. And then if you say, well, all I have to do is take that distance and divide it by the time that it takes to get around the circle, and I have the velocity in meters per second. Now that time that it takes to go around the circle once is commonly referred to as the period. Capital T they use for that. That's why I use capital T and not little t down there. And that is the period. And that is the amount of time for an event to occur. In this case, one rotation of a circle. Another way that you can talk about rotational speed, like the velocity that you're going, is in angular speed. Angular speed, and that's easily defined as omega. Now that looks like just a regular W, but it's really not. It's the Greek symbol for the lowercase omega. You might be familiar with that as your uppercase. And it's pretty simple. It's measured in radians, because angles per second. So this unit, we want to have it here, radians per second. So radians is what I like to use. And then that would be 2 pi, as I sort of defined earlier, except for I just used it as 6.28, but 2 pi over the period. So basically the same exact thing as before, except for now you're just defining that it goes around. Now, but the biggest difference here is that if you define the angular speed, every object on that that is going in that circle, so if you looked at r, so anything along that line r that's sweeping out a circle, so imagine if these were all sweeping out circles, they would all have the same angular speed, but they would not have the same tangential velocity, because remember that's dependent upon, if you go back and look at the previous equation, it's dependent upon the radius. So the larger the radius gets, the larger the tangential velocity. So so that means that anything that's in a circle is accelerating, and there's a relationship between acceleration and we call that the acceleration that you feel because you're in a circle and you're changing direction is called acceleration centripetal. And this is basically center seeking. So in other words, it's an acceleration towards the center. And so there, if you have an acceleration centripetal, then you must have, remember, if you're accelerating towards the center, the only way you could be accelerating towards the center is if there is a force acting on you, and that would be called force centripetal. And this is, you never actually label anything force centripetal. This is just a term given to the force that is causing you to stay in circular motion. So for instance, a ball at the end of a string that you're spinning around and it's going in circular motion, or a car going around a corner, its tires are pushing you towards the center, and they're pushing out, but friction's pushing back against them, and they're pushing you towards the center of a circle. You know, just one of that ride at the fair where you stand against the wall, and the floor sort of drops out, and you're going in a circle. The wall is the normal force, and the normal force is now causing it. Gravity is causing the moon to stay in circular motion around Earth. So notice I never said, oh, there's a force centripetal that's causing that. It's actually always caused by something else. So force centripetal is just the word or term given to the force that's causing an object to stay in circular motion and causing centripetal acceleration, or acceleration towards the center of a circle. So so you can write an equation for, there's a lot of derivations here, but it gets pretty messy. But I'm just going to go through the basics here. You can talk about acceleration centripetal as being the relationship, the velocity squared divided by the radius of the circle. And if that's valid, then you can also write a statement of Newton's second law that F equal ma sub c. So that means you have force centripetal. So therefore you could write m times the velocity, tangential is what I sort of like to refer to it, squared over the radius of the circle. And you can use little r. I just use big R in this caption here. But I am going to stop this. Well, no, I'm going to do one more thing. I'm going to talk to you about period and frequency. I think I got that right. Okay, period and frequency. So there's a relationship between these two. So earlier I was talking about how an object went around a circle. I think it was, I hope I got my math right on that one earlier. It went 360 degrees in 2 seconds. Yeah, and so what if you went around 10 rotations in 5 seconds? So you did 10 rotations in 5 seconds. 5 seconds. So this is easy stuff. So how many rotations per second are you doing? Well, you're doing 10 divided by 5, or 2 rotations per second. And so if you were to look at that in terms of angular speed, that would be 2 times, what was that, 2 pi, is that right? So it'd be 4 pi radians per second, if I'm not mistaken. You can check my math. If I'm wrong, we'll correct it. But so this is the frequency. This is the rate at which the event, how many times it occurs per unit time. And so this is, I'm going to get rid of that part right there. This is the frequency. And that's so we're going to abbreviate that as F. And there is a relationship between frequency and period. So how long did it take for one event to take place? If 2 rotations took place in 1 second, then how long would it take for one? And the relationship between frequency and period is just merely the reciprocal. They are the reciprocals of each other. So if you take the period, if you take the frequency and you solve this for period, you get t equals 1 over f. So if you put that in, just think of the math real quick. You would have t equals 1 over 2 rotations per second. So that means it'd be 1/2, but you would invert the units and you'd have seconds per rotation. So that'd be 0.5 seconds per rotation. See if you can listen to that again and it'll make sense, but they're just reciprocals of each other. So if you're given a frequency, what I'm trying to point out is that you always are given the period as well, or vice versa, by this simple little relationship down here. One measures in events per unit time, rotations, revolutions, degrees. The other is given to you in seconds per event or seconds per rotation. So 2 simple things to grasp on rotational motion. And I'll stop with rotational motion there. We'll probably get some more in later in the week.